Hello everyone, my name is Norma Quecano and I'm here to talk about support vector machines. A support vector machine is a supervised machine learning algorithm used for both classification and regression tasks. It's capable of performing linear or non-linear classification, regression, and even outlier detection. Once trained, the SVM can be used to predict the class labels of new unseen data points by evaluating which side of the hyperplane they fall on. We want a classifier that, given a pair of XY coordinates, predicts where the data point will fall on. There are several advantages to this system. It's effective in high-dimensional spaces, it's memory efficient, it's versatile, it's sensitive to the choice of hyperparameters, and it's a powerful algorithm for classification tasks. Here's how SVM works for classification. It starts with data representation. SVM works with labeled training data. Each training example consists of an input feature vector and a corresponding class label. And then it finds the optimal hyperplane. SVM aims to find the optimal hyperplane that best separates the classes in the feature space. In the case of a binary classification problem, this hyperplane is the one that maximizes the margin, which is the distance between the hyperplane and the nearest data points from each class. These data points are called support vectors. Finally, margin maximization. The optimal hyperplane is chosen to maximize the margin, which provides robustness to the model by maximizing the separation between classes and reducing overfitting. In this simple example, the data is linearly separable. We can draw a straight line to separate red and blue. When data is linearly separable, SVM with a hard margin is used. In this case, no misclassifications are allowed, and the goal is to maximize the distance between two parallel hyperplanes that define the margin. The optimal hyperplane is the one with the largest margin. When data is not perfectly separable or when some misclassifications are acceptable, we use soft margin SVM. SVM can handle nonlinear cases using a technique called the kernel trick. Common kernel functions include linear, polynomial, radial basis function (RBF), and sigmoid kernels. Soft margin SVMs accommodate imperfectly separable data or acceptable misclassifications. It offers a flexible boundary, balancing margin width and misclassifications via the hyperparameter C for optimal performance in real-world scenarios. SVM is used in the real world in anomaly detection, for intrusion detection in cybersecurity, or fault diagnosis in industrial systems. It's also used in finance for stock market predictions, credit scoring and fraud detection, or in handwriting recognition for optical character recognition and digitizing handwritten documents. It's also used in social media as a sentiment analysis and trend detection, and in remote sensing for land cover classification, vegetation mapping, and environmental monitoring. We can also see how it's used in credit card fraud detection. Financial institutions deploy SVM-based systems for real-time transaction monitoring, leveraging its ability to discern intricate decision boundaries to combat credit card fraud effectively, thus protecting users' finances. SVMs are essential in spotting credit card fraud. They work in a feature space representing transactions, focusing on attributes like amount and time. SVM finds a decision boundary crucial for distinguishing fraud from legit transactions, maximizing the margin between them. Using kernel functions, SVM handles nonlinear patterns effectively. This helps financial institutions detect potential frauds early, protecting both cardholders and institutions. Overall, support vector machines are pivotal across various domains, offering effective classification and robust decision boundaries. Whether in credit card fraud detection or other applications, SVM's ability to handle nonlinear patterns ensures proactive problem solving, contributing to the security and efficiency of diverse systems and processes.